Hey guys, welcome to another edition of Calculus BC via the internet. We today are going to learn our first section of first day of section 3. So remember how I told you that we are kind of like still in calculus land, but we're going to do like each little land. We've already covered parametric land, we've already covered vector land, and now we're going to veer our way to polar land. And so as we get into polar land, what we're going to do is we are going to take one day, just one day, and we're going to review how to graph some polar curves that we learned in pre-calc last year. So we're going to do a one-day review. We're going to do the notes super quick. All of it should sound like vaguely familiar to you. Be like, yeah, I do remember that. We'll talk about some fun hints to help you remember how to graph things, because you do need to know how to graph some of these guys by hand. And then in the future lessons, we're going to go ahead and get into the calculus with polar. So let's go ahead and get my PowerPoint all shared up here. And let's do this. So here we go. Our fun title for today is going to be called Back to the Polar, going with our movie theme. And I hope that you saw the note in Google Classroom that says you need to download a different paper for the notes. We made some changes and did not reflect that in the note packet. Totally my fault. And so hopefully you went ahead and did that. And then also the worksheet for homework is also attached to Google Classroom. So there are 3 major types of graphs that you should know how to graph by hand for the AP exam. And they are petal graphs or roses, limicons, and limnoscates. We're also going to toss in circles because we do like to do circles a lot. So the first graph is called petal graphs or roses. And a fun way to remember this, because we're all about the fun ways to just try to make it stick in our brains, right? We don't want it leaking out. That would be so silly. Is we're going to say that we're going to take times to smell the roses. I mean, kind of silly, but it's totally going to work. So why did I say take times? It's because there's no plus signs or anything in these equations of R equals. Remember in polar, your 2 variables are a radius and a theta. And so our equations are always R equals and then something with theta. And so these first type are called petal graphs. And when you look at each petal or each petal graph, they're going to be like a loopy around guy. It looks like a flower. We need to figure out how big to make it and how many petals there are. So the radius length of the petal is going to be A. And so we just get that number from right here in the front. Okay, so this guy right here, so this is A, and that determines your petal length. And here's A right there. It doesn't really matter if it's sine or cosine. That's the petal length. There's 2 types, and it depends on if it's going to be a cosine graph or a sine graph, right? That totally depends. So for the cosine graph, it actually, the first peak starts there at 0. And so you put up your, your first guy has a loop right there on the x-axis, the positive x-axis. Also for sine, your first peak is a little bit offset. And so how much do you offset it? How much is it tilted? You take pi and you divide it by 2 times whatever n is. I always like to have little fun ways to remember it, because this is a lot of really ticky-tack information. And so if I can remember this one, I say to myself that you're going to have pi and then for 2 people. And then that's how I remember how to do this one. So pi for 2 people. Nice way to remember it. And then we have to figure out the number of petals. So if n is an odd number, okay, so an odd number, you're going to think to yourself, odd man out, and then that is the number of petals. So if it's 3 or 5 or 7 or 9, whatever, usually we keep the number small, like 3 and 5, then that's how many petals it's going to have. Now, what if n is even? Well, if n is even, I want you to channel even Steven. That's what I want you to travel, even Steven. And then now there's double the amount. So even and Steven are buddies, and then it's double the amount. So here's the weird thing about it. It's that it's actually always 2n. it's already written for you. But in the odd cases, it graphs on top of itself, and then it actually goes around 2 times. So normally, like the period for all this stuff happening is 0 to 2 pi. But when it's an odd, it actually completes the cycle in only 0 to pi. It's kind of interesting like that. Okay, so let's do some example. Oh, I forgot one thing. Seriously, Mrs. Fox, gotta pay attention. My brain's all scrambled. And so how far apart are the petals? You just need to think to yourself, when you do your radians, it's 2 pi around, and you just need to divide by the number of petals because you want them all evenly spaced out. So that should like kind of make sense. Okay, so for our first example, I know that it's a petal graph because everything is multiplied right here. Nothing's added. And so we're just going to go through the pieces and kind of like write down what the graph should look like, okay? So the maximum radius out, like the length of the petal, is going to be this first number right here, and so that's going to be a 6. Okay, how many petals is it going to have? We draw our attention to this number right here, and this is an odd number, so it's going to be 3 petals. Remember, odd man out. Okay, where's the first peak? Well, this we get because it's at a cosine. So because it's cosine, it's going to start right there at the positive x-axis when theta equals 0, or just write x-axis if you want to. And then how far apart are they? So we go up and we think about the number of oh, that was so sloppy. Let's pretend like that actually went around the 3. Again, so silly, Mrs. Fox. And so the number 3, we're going to take 2 pi and then divide by 3. Now, what I also might want to do is when you look at a piece of polar graph paper that they give you, all of these little spikes out are actually multiples of pi over 12. So sometimes what I like to do is I like to turn this into a multiple of pi over 12 just for counting purposes. And so it's very helpful. And so what we're going to do is we're going to put a 12 on the bottom, and then we're going to put an 8 pi on the top. So we're going to put an 8 pi on the top, a 12 on the bottom, and then that is how far apart we're going to make it. So let's go ahead and graph this. We're going to plot some points. It goes through the origin when we make our petal graphs. I'm going to count out 6 on the x-axis and put a dot. I'm going to go around in a circle, and I'm going to go 1, 2, 3, 4, 5, 6, 7, and 8. And then I put my next dot and then do 8 again. And you make the graph. So really, this is how you're supposed to graph it. This is going to be a catastrophe, you guys. Okay, I'm drawing it with the mouse on my laptop. So just follow the pattern. But basically, it starts over here. You go to the center, and then you go to the other point, and then you go back to the center, and then you go to the other point, and then you go back to the center, and then you go to the other point. So I'm going to erase all of that because that looks super amazeballs. And then here's what the graph looks like. I mean, seriously, isn't that gorgeous? Nice, right? So that's what it looks like, and we have made one graph. Okay, let's do another one. Here we go. So example number 2, it says 5 sine of 2 theta. So you see how I'm mixing it up. Okay, we could probably do this one just a teensy bit faster. The length of the petal, the maximum radius out, is going to be 5. We're getting it right here from this 5 in the front. Okay, then how many petals is there? Next to the theta, there is a 2. 2 is an even number. So it's even and Steven are buddies. So we go ahead and we make that 4 petals. Where's the first peak? We see here it's a sine graph, so it's going to be offset a little bit. How much is it offset? It's going to be pi and then 2 times this number right here, right? This value right here, so 2. And so the first peak is at pi over 4. And then how far apart are these babies? So you're going to take 2 pi and divide by the number of petals, okay? So 2 pi divided by 4 actually is pi over 2. Again, that's how far apart they are. So just like a quarter turn, I might want to think to myself, what is that in 12ths? And so in 12ths, if I am counting, this would be 6 pi over 12. So if you want to think about this in 12ths when you graph it, please be my guest. Let's graph this baby. So at the pi over 4, guys, so at this pi over 4 right here, okay, that's going to be our first peak. It definitely goes to the origin. I'm going to count out 1, 2, 3, 4, 5, put a dot. And then I'm going to count 6 spikes. So 1, 2, 3, 4, 5, 6. We're going to put another dot, count 6 again, put a dot, count 6 again, put a dot. It does loop around like I showed you before. I'm only going to start it because it's really hard. So you would start it like this, and it would go here, and it just goes to the next petal. Whoa, a little earthquake happened there. Whoops, a daisies. And then it just keeps going around and around and around and around, and boom, just like that. Of course, you're going to make that look way better. And here it is when we look for it. Whoop, whoop, looks gorgeous. All right, so that is how you graph your petal graphs. Let's move on. Go ahead and go to the next type. And that is a limaçon. Limaçon is the French word for a snail. So these are like very roundy, snaily looking things. Sometimes they look like tomatoes or butt cheeks or, fun things like that. And so these guys, you can tell that these are different than the ones that we previously did. Where did my little drawing thing go? Because now we have some pluses and minuses in here, okay? So there's going to be two values, and it's going to be an A value and a B value, and then we have some sort of addition or subtraction happening. And so if it's a cosine, it means that this limaçon is oriented on like the x-axis. Now, it matters what the middle is, right? So when the middle, this sign right here, is a positive number, then most of the shape is graphed towards the right. If it's a negative, then most of it is graphed to the left. It's like that's where the bulk of the shape lives, is on the right or the left. Now, if it's a sine, it's going to be the bulk of the shape is on the y-axis. If the operation in the middle is a positive, it's mostly up, and if the operation is a negative, then it's mostly down. Okay, so we've got how it's oriented and where most of the shape lives. Then the next thing we have to find are some values, okay? So there are certain lengths that you need to find. There's going to be 4 of them where you have to place the point. So there's always a larger side, a smaller side, and then what I like to call the bumps, just of like what the shape looks like. So the larger side, what you're going to do is you're going to go ahead and add A and B. Now, I'm being a little bit lax right now. Technically, guys, this is the absolute value of the A and the B that you're adding together, okay? So you are ignoring the sign in the middle. This sign does not mean anything when we're trying to find these values. You're just adding what the A and the B are. And so you're going to add for the larger part. You're going to subtract them, A minus B, for the smaller side. And then those bumps, the aforementioned bumps, are going to be at the A value. The A value is the guy in the front, okay? So now this brings us to what kinds are there, right? So of course I have silly ways to remember them, but there are four types of limaçons, and it depends on how A and B are, like how closely they're related to each other, meaning like which one's bigger than the other. So one of the types is a cardioid. Okay, remember we're ignoring the plus signs and the minus signs. It doesn't actually matter. So a cardioid happens when the A and the B value are the same. Okay, when the A and the B value are the same. So I like to think of this as having a nice, steady heartbeat. Just like boom, 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 boom. Boom. Okay. And cardio in it, which means heart. So that's what we're going to talk about. Okay. So a nice, healthy, steady heartbeat. Now, the looped limaçon, okay? So the looped limaçon is going to be when the guy in the front is smaller than the second guy. So when the A value is less than the B value, okay? And so on this one, the only thing I could think of for this one is that when the number's smaller in the front, I thought to myself, like when a small person can loop over. It's a thing I used to do with my kids when they were littler. I can't do it right now because they're way too big. But when they were littler, I could do this. So I have a video just to show you, like in my head, how I remembered having the smaller number in the front. So here goes Cassidy. She's going to loop over and just like that. And the only way that she's able to loop around is because she is smaller than me. If she was bigger than me, I wouldn't be able to loop her around. Okay, so then there's the dented limaçon, okay? So for the next two, we are going to think to ourselves for how it works is that we are going to pretend that we are hanging out with our friends in our driveway, of course, observing all social distancing rules, and we are 6 feet apart from each other. Of course, of course. And so what happens for your dented limison is when that A value is just slightly larger than B, okay? So we're talking slightly larger. There is a threshold for slightly larger. It becomes after 2 times bigger. We call it way bigger. And so when A is slightly larger, you say to your friends, oh yes, sure, sit anywhere. And since your car is in the driveway, you are going to go ahead and let your friend sit who is slightly larger than you. And then you know what happens? Oh my goodness, your slightly bigger friend dents your hood of the car. I can't even believe that happened. And so that's how I'm going to remember it. So when A is slightly larger, your slightly larger friend sits on the hood of your car and dents it. Okay. But then, okay, what if A is way larger than B? Okay. Way larger. And that means it's at least twice as big. Okay. So when it's at least twice as big, you would never in a million years say friend who I am, standing 6 feet away from. Of course, that joke never gets old. Okay, you're going to say, you don't get to sit on the hood of my car. You have to sit on this very nice flat bench. Okay, so they get a flat bench to sit on, and then that is the shape of the graph is it has a flat piece to it, and that's how we're going to remember it. Okay, we got this. So let's do some examples. Let's do this. So this guy right here, when we look at the 3 and the 4, we're going to figure out how it's oriented, how big to view the pieces, where to put it, all that good jazz. So where is this guy oriented? Okay, so because it's a cosine and because it's a plus sign, okay, it's oriented on the x-axis and it's oriented to the right. That's like the positive x-axis. Okay, what shape is it? The 3 right here is smaller than the 4. And so we know that that means that it's a looped limison. Okay, now something else that is not, there's not like a space for it, but I want you to write it down is I want you to write to yourself, I want you to write the small and I want you to write the large and I want you to write where the bumps are going to be. Okay, so what is the smaller edge of this, the smaller value? You're going to subtract the numbers. So 3 take away 4 is a -1. So it's actually going to loop into itself, like back into itself. The larger part is we're going to add the 2 numbers, and 3 plus 4 is 7. And then where is the value of the bumps? It's going to be a 3, okay, because that is in fact the very first value. So let's see if we can put this on our polar piece of graph paper. So we are going to, it does actually go through the origin. Okay, that larger side is on the positive x-axis. So I count out 7, 1, 2, 3, 4, 5, 6, 7, and I put a dot. It goes into itself, a -1. And then on the opposite axis where it's not the most of the shape, that's where, quote, the bumps go. So the bumps are going to go up 3 and down 3, and then we're going to attempt to draw this. I will try to draw this on the thing, and then I will erase it. But it looks like this. It goes around. Oh, heavens to Betsy. That is the worst thing I've seen in my life. Oh, man, even my soundboard's laughing at me. And so that's kind of what it looks like, of course, without all the messy things. So this is what it really looks like in person. I am actually going to try to erase all of that because that is ugly. And let's go ahead and switch that to what it really looks like. And that's what it looks like. Okay. Gorgeous graph. All right, let's go to the next guy. And so now we look at our numbers and we can see on our numbers that we now have a 4 and a 4. Oh, okay. So these babies are the same number. So we're thinking nice, steady heartbeat. So it's going to be a cardioid. Okay. We look and we see that there's a negative right here and a sign. So it's oriented most of the shape. The bulk of the shape is on the y-axis and it is down. Okay. So it's going to be like on the negative y-axis. We already discussed that it was a cardioid. So that looks lovely. And then let's go ahead and put the small, the large, and the bumps. Like, what are those values? Okay. When I subtract the 2 numbers of 4 minus 4, I get a 0. When I add 4 and 4, I get an 8. The bumps are always the very first number. So that's going to be a 4. Oh, that was a crazy looking 4. Okay. It kind of looks like a kindergartner is drawing these things. I'm so sorry, guys. who let the kindergartner teach these notes? Okay, so here's how it looks. We go through the origin. The bulk, right, is down there on the negative y-axis, so that's why I counted to 8. The bumps are on the opposite axis, so at 4 and 4, and then you try to just make it look as bumpy and as heart-like as you can. It's very tomato-y shaped, if you ask me. So it goes kind of fat like this. It comes down here. It's pretty wide, and bink, that's what it looks like. And there it is. Let me get the bad one erased off of this baby. And there you are, guys. So that's what it looks like. Let's go to example number 5. I'm trying to do one example of each so we can just make sure we know what it looks like. So this guy right here has a 5 and a 3. Those are the numbers we're going to latch on to. Where is this guy oriented? There is a negative and a cosine. And so it's on the x-axis, and it is mostly to the left. The bulk of the shape will be on the negative x-axis. Our shape, the 5 is what we would call slightly larger than 3 because it's not twice as big, and so this is the dented one. Again, we will do before we do our polar graph, we're going to have to figure out what the small length is, the large length, and then what is the bumps at, okay? And so the small, we're going to go 5, take away 3, we're going to put a 2. For the large, we add those two numbers, and 5 plus 3 is an 8, and then the bumps are that first number, so they are at 5. So this one does not go through the origin. So that larger side is going to be on the negative x-axis. We go all the way to 8. On the flip side, on the other side, we go to a 2. And then the bumps on the y-axis are going to be at 5 and 5. And so we draw this guy. We just draw it slightly dented in this spot right here. So it's dented, and then it loops around and goes, and it's gorgeous. And it's not bumpy like that, but, you know, something of that nature. And then that's what it looks like in real life. All right, looking good, looking good. Let's go ahead and come on, erase my guy. Oh, there it goes. Whew. Could not bear to live with that guy anymore. Okay, let's go ahead and do the very last example, and then we will go to the third page of notes. Whew, so many fun graphs we're making right now. So this next guy, if we look at our numbers, okay, we have some fun numbers. We've got a 6, we've got a 2. And so this 6 is way larger than 2. It's more than double. And then we've got the plus and the sign. So we've got the sign and a positive. So it's going to be on the y-axis and up on the positive y-axis. What shape is it? We already talked about that 6 is way bigger than 2. So that means it's a convex. It has a flat piece to it. And then again, I think it would be wise if we figured out the small value, the large value, and then what the bumps are at, okay? The small value, we're going to subtract the numbers. A 6 take away a 2 is a 4. We're going to add those 6 and 2, and we get 8. And then the bumps are at the first number, so that's a 6. And that means we have this. Here's our up there on the y-axis. Again, does not go through the origin. We counted to 8. On the flip side, down there, we counted to 4. The bumps are on the x-axis, so we're going to go to 6 and 6. When you draw it, you're going to draw this like a little bit flat, kind of exaggerate it so that you know that that's like flat right there. And then you're just going to make it go around. This one always surprises me how like circular it is. It just kind of looks like a, you know, like a ball that's been like, you know, like one of those bouncy balls like from the handball court that has the air out of it just a little bit. It's like a little bit flat. You know, like just flat. Yeah, that's kind of what it looks like to me. It looks like a flat bowl. And so let's go ahead and see what this guy looks like. And it would look something like that. So it looks very circular. For me, would probably exaggerate the flatness of the guy down here. Okay. Let's go ahead then and go to another type. So another type. So go ahead and turn to the page. And we are going to learn about lemniscates now. So lemniscates, the way that I remember a lemniscate is that I say to myself, you lemniscate in a figure 8 on a double date. So fun. So clever. I know, just the coolest. And so how do I remember this? Well, there is for the equation, there's an r squared, and then this right here is a 2. Those are the dead giveaways. So to me, it's like there's 2 thetas and 2 r's, and they're double dating, and then it looks lovely like that. And that's how you will recognize that it's a lemniscate. Okay, cosine lemniscates are always oriented on the x-axis. And again, it's just going to be a figure 8. The sine lemniscates are always just perfectly diagonally tilted, basically on the line y equals x, but we're in polar. So it's on theta equals pi over 4. The maximum distance that we go out is going to be whatever the square root of this number is right here. In fact, in pre-calc, I think we said that this number was a squared, and then, the maximum distance out was a. It doesn't really matter. Just, guys, whatever the front number is, to take the square root of it, okay? And then that's how big, like, the loops are on your lemniscate. We are going to do one example of this because this is like so easy. And we're going to say that because this is a sine, it's oriented on the line theta equals pi over 4. How far out are we going to be? It's just going to be the square root of 25, which is 5. And so on our polar piece of graph paper, we're going to count out, it goes to the origin, count out 5 on theta equals pi over 4, go to the 5 pi over 4, and then I'm not even going to attempt to draw this one. It looks like that. So nice, so easy, and gorgeous. Okay, we have one more type to go. Here we go. Circles. When we do our circles, it's going to be super easy, okay? The circles will have just a number in front of the sine or the cosine, and then notice that this theta right here is all alone, okay? There is no number with the theta. Okay, but that's all right. You just know that it's going to be a circle, okay? And then what are the things that we need to write down for this? So if it's going to be like on the x-axis, it's going to be for cosine, okay? The guys that are on the y-axis are going to be for sine. When you have your x-axis, if it's positive a, oh shoot, where's my little pointer? There it goes. Okay, if this a right here is positive, then it's definitely going to be to the right. If it's negative, it's going to be to the left. Now, similarly, okay, for the y-axis, if it's a positive, it's going to be up, and if it's a negative, it's going to be down. How big do you make these circles? Well, A is going to represent not the radius, but the diameter, okay? So it's the diameter. So you're kind of just like plotting the edges. It's always going to go for these circles through the origin and then out however far A is. It's kind of like making like one big fat one-petaled graph. Okay, we have 2 examples and we are done. Okay, so here we go. This says r equals -5 cosine of theta. Okay, it's oriented because it is cosine. It's going to be on the x-axis. Because of this negative right here, it's going to be towards the left. Okay, how big are we going to make the diameter? I actually want you to write this down. I don't think I actually put this on here, but go ahead and write this down. The diameter is going to be equal to 5. And so let's go ahead and figure out how to graph that. Goes to the origin. I'm going to go to the left 5. And then just like that, circle. So easy, so gorgeous. When I draw these by hand, sometimes they look like pancakes. It's fine. We'll know what you mean. Just do the best circle that you can. Okay, last example. Okay, if r equals 8 sine of theta, okay, where's this guy going to be oriented? So because it's a sine and because there's technically a positive right here in front, it is going to be on the y-axis and mostly towards the up. Okay, what is the diameter for this guy? So right there, pointing, I already did it. The diameter is that number in the front, and so the diameter is going to be 8. Let's graph this baby up, and we will be all finished. Goes to the origin, count 8 up because of the sign and it being a positive 8, and then just like that, circle. Totally easy. Okay, ladies and gentlemen, this is the end of your notes, okay? You were actually doing a polar graphing worksheet, which you will have to download. When you take your picture of it, if you don't send me 2 pictures if you don't have to, maybe just like put the pages side by side if you don't print it back to back, but it's going to be just like amazing. So tomorrow, or what, not tomorrow, I don't know when you're going to watch the next lesson. So whenever you watch the next lesson, you're now going to be doing calculus with our polar, okay? And so when we do our calculus with our polar, it is going to be amazing, amazing, amazing. I think you're going to have a really fun time with it. It's going to be fun. And so I think that is the end of our lesson, okay? Hope you guys had a fun time. I'd like to thank my sound producer for helping me with today's lesson. I know it was a good thing. And so that's it, guys. I'm going to send you away with a fun little, trumpet fanfare. And I hope that you guys have a wonderful rest of your day. Bye.